So welcome to the afternoon session. This is exceptional. We'll have this afternoon session only today. I know this is a long day today. We'll be done by about 6. About neurodynamics, so the second path. In this exercise session, early this afternoon, you dug deeper into behavioral dynamics. I talked about that as the last module in the morning, and now we'll start in parallel, sort of a redoing the same elementary things, attractors and bifurcations, now for neural activation variables. And this, you will see how all of this comes together tomorrow. So in the Breitenberg lecture this morning, I talked about internal loops in the feed-forward system, where the sensory information would not be passed directly to the motors, but would potentially circle in a neural network. And now I want to make that formal. And to make that formal, I'll have to represent the state of that neural network, somewhat like the behavioral variables this morning represent the state of the system in the world. And that's where the activation concept comes in. You will see that that is throughout all neural modeling, connections modeling, and so on. This is an issue of describing the inner state of the nervous system. There is now a big literature in computational neuroscience where people use variables that are close to the biophysics of neurons. For instance, people model the membrane potential, for instance, in the dendritic tree or near the cell soma where the spike generation occurs. And they think of that as sort of a privileged level of description to understand what an individual neuron does. While a lot of traditional modeling has taken the extracellular perspective and said spikes are the only things that really have effects on other parts of the nervous system. There's some exceptions, electrical synapses, but for the most part, it is all the synapses are based on spikes, and therefore we take a description of the spike train as a privileged level of description. Some of that debate currently is quite reductionist in nature. That is, people somehow think the smaller, the more fundamental. If you think through that, you recognize that that's not a reasonable perspective. In fact, the membrane potential itself is a collective effect. Of course, in the membrane, there are, for those of you who know anything about neuroscience, you might know there are these ion pumps that actually bring about the membrane potential. And you could say the ion pumps are essentially big macromolecules in the membrane that change their configuration as a function of the voltage they sense and some other signals like chemical signals. And then you would say, well, that is the right microscopic description. And then, of course, you could go down that chain until you hit quantum mechanics. So at some point, you have to fix the level of description. And the appropriate recipe for that is to say that's the level of description at which there is the amount of invariance I need to understand the phenomena I'll be looking at. And so we'll be looking at behavior, at cognition, at sensory motor, perception, motors, that are the things I introduced this morning. And my upshot will be tomorrow that the level of population activation, that is looking at some state variable for a lot of neurons that represent similar things that are in the same cortical area, maybe have similar tuning curves and so on, that is the best correlate with behavior. And that's why we use this particular level of description. Even if you're talking about population, you still have to say, how do I compute population activation? I'll show you that formally tomorrow. So for now, I will be using a continuous variable that I call activation that will ultimately be computed from spiking activity of many neurons that are somewhat redundant, that are overlapping in their tuning curves, for instance. And if you think about this more abstractly, then it's really the sigmoid function that defines what activation is. So you could almost consider that to be an axiom of this particular neurally based approach, that we say that variable that the sigmoid is a function of and that determines whether a state variable has impact on downstream functions, that is the right activation variable. So the sigmoid function is a function of this activation variable that is nonlinear. It approaches 0 for sufficiently negative levels of activation and approaches some constant that we often normalize to 1 for sufficiently positive levels of activation. That we choose the transition to occur around 0 is essentially defining what 0 means. It's a calibrating that activation axis. We could do that around any other value, and that will be then another parameter in the model, and we just conventionally use 0. If you think of the activation as being computed from firing rates, those are positive numbers, right? These are rates, spikes per second. So it's not obvious how you can get negative firing rates, but the answer is that neurons have spontaneous firing rates. And I should say from tomorrow we have this lecture downstairs. Did everyone hear that already? I'll say that in the end of the lecture. Because this construction work, it will keep going this whole week apparently. I didn't know they were going to hammer. I asked them to make an exception today, but no, it's never perfect. So I was saying spontaneous firing rates occur in the absence of any particular input or any particular task to the neural population, and by subtracting from firing rates that spontaneous firing rate, you can get negative numbers. You will see in the construction that it's actually even more abstract. There are more normalization steps going from firing rates to these activation variables, so there's ample room for negative numbers showing up. It's important because if you have a variable that's bounded to below, the mathematics changes and makes complications that we don't want to face. I said nonlinear function, and what you really see, it's a monotonic function that increases monotonically. It can be almost step-like or smoother, and that's a parameter beta that measures the smoothness of the sigmoid. And we, in our models, use a particular form of it, sometimes called the Boltzmann form, but that doesn't really matter. Most of the results that we have don't really depend on the exact function of form. Such a function is nonlinear in some strong sense, and you will see that in about half an hour. You will really get an operational definition for that. Just wanted to allude to intuition now. It's nonlinear in the sense that it has properties that any linear function cannot have. For instance, it has the property that it goes to a constant and at minus infinity, and then goes to a different constant and plus infinity. And the linear function will go to plus minus infinity, or if it goes to a constant, it's the same. It will be horizontal, straight line. That will be the same constant left or right. And that's important. So you can see you can't really approximate this by a polynomial. And that's what I earlier referred to as being sort of the weak nonlinearities, is like constant plus a linear function plus a quadratic and so on. So we can perturbatively build nonlinearities. This kind of thing would require infinitely many terms like that. It's, that has impact on the dynamics that result from that. So that's the axiom that we're postulating, that only the sigmoided activation, that activation that passes through this function, we call this G of u, only these kinds of activations are supposed to show up anywhere downstream from a particular neuron that we look at. So downstream meaning, on neurons that this particular neuron we look at makes a synaptic connection on, or ultimately on the motor system. So negative levels of activation will not get transmitted. That's a principle that we postulate for neurodynamics, and that's neurally plausible, of course, and that actually has significant effects. It's not a principle that's in any way debated. It is a reason, I just to illustrate, how that principle is pervasive. This is, for instance, the reason why in the nervous system you will very often find that the number of cells that you have to represent a particular parameter is doubled. I could give you an example, a classic example from the literature. You have, for instance, hair cells on insects that are sensitive to where the wind comes from. They are attuned to the direction in which the hair is bent. And there are some cells that are tuned to, it turns out they're tuned to sort of 45 degrees. and some that are tuned to minus 45, and some that are tuned to 200 and whatever that is, and the other quadrant, and that's twice as many as you need, because if you want to represent the direction of wind, it should be enough to have a sinus and a cosine. There will be two cells that are sinus tuned and cosine tuned around. Sinus and cosine would be 90 degrees against each other. And the reason why the nervous system has twice as many is that it can't do the negative. It needs to represent everything with positive activity, because neurons don't transmit their negative activity. And that means that where the minus part of the cosine multiplied with a negative number gives you a positive bulge there, you need an extra neuron for that. And that's a principle you find pretty much everywhere in the nervous system. So this is a fairly solid piece of evidence that we have that principle. This shows up, for instance, for those who know such things, in non-negative matrix factorization. Anybody knows that? Compared to principal component analysis. So some of you might know that you can decompose signals with principal component analysis into elementary variables, but from which you then can reconstruct the signal. But when you reconstruct, you use negative coefficients potentially to cancel, plus and minus things cancel. And that's not a good model of the nervous system, and instead non-negative matrix factorization is the version in which all the contributions have to have a positive coefficient, so you can't do cancellation. So there is a more abstract way. I'm just hinting at that. You don't have to, it's not important for the rest that you know these abstract elements. So I was saying that there is a way of identifying what these activation variables are that is more abstract than postulating a particular biophysical level of description. Tomorrow you will actually see that there's another level of abstraction that I'm sweeping under the rug right now. That's also fun. Okay, that's activation. Activation is commonly used in neural network kind of models. In connectionism, they're using activation concept, and sometimes connectionists sort of pretend that it's very biophysically real, but that's just superficial talk. It's really the same kind of activation concept as we are using here, and they sometimes haven't thought so deeply about its deeper meaning. Actually, it's not true for all. There is some very good texts. I cite that sometimes where people think about it deeply. So it's the same concept. They weren't forced to think about it as much as we were. This contrasts to the use of activation as a concept in some classical information processing accounts in psychology. So those of you who know what ACT-R is or what SOAR is, S-O-A-R, cognitive architecture, anybody knows that or is familiar with that? Yeah. So they also use an activation concept, and that is a little more subtle what that relationship is. It is not literally the same. It has some relationship. In a way, what's common is they also have a function that measures how far a particular information processing model is from having impact, from emitting its output. But it is the mechanism of how that output is brought about is a separate one. It's not through the activation. The activation just says whether the output will happen soon, but the output is actually information processing, namely delivering a message. And this is, I say that, I'll say that several times, but here I use that opportunity. This is the fundamental difference between information processing and neural networks. Neural networks, you only have activation. You can't send a message. The only message you send is activation. You can't send any contents. You have to make sure that the activation brings about the contents. And while in the computer metaphor, you can really there is the thing that you can say that you will be sending a message now. For instance, in packet switching, you might know there are these control signals that reflect that now a signal comes. But you also send some contents, right? That content is sometimes called a pointer, where you say where the other processor should look for the information, or it can be called by value, where you actually transmit the information. And that's not possible in the nervous system. Among the neurons don't send each other other messages than just that they are firing. That's the only thing they know. And that is a major constraint. Okay, that's the activation concept. Now, activation dynamics, I have an abstract argument for that, and I'll cut that relatively short. I'll have to talk about two things. First, that activation evolves in time, and I will argue it actually evolves continuously in time. And then second, that there is something about stability, that activation again has stable states. That's a somewhat abstract argument that I'll make in a moment. Now, that activation evolves continuously in time, ultimately the evidence for that is from the fact that behavior evolves continuously in time. And for instance, it does not evolve discretely in the same sense in which spikes are discrete. There is no empirical evidence for the discrete nature of spiking somehow being reflected in discrete behavior, that you would have a certain kind of sudden onset of something. An empirical example of that is continuous online updating for movement. There are, of course, discrete events, like you start a movement, or you suddenly understand, or you suddenly detect something. These are seemingly discrete events. But they are embedding continuous time in the sense they can happen anytime. It's not like there is some kind of discreteness, a grid on which only they can then happen. Online updating illustrates this very well. Online updating is a phenomenon in motor control in which a participant tries to point at a target. That target, for instance, might be illuminated at some point, and that triggers the response. So, that's the go signal to make that reach. And then at some point in the movement preparation, in the process of movement preparation, or during the movement, you actually just suddenly shift the target to a new location. And what will happen is that the participant will then update the movement plan to the new target. The update will start about 100 milliseconds after the jump. So there's some delay for that. But it can happen any time. So if you shift the time when the target jumps, the point where the correction occurs shifts with that, in some sense continuously. And that shows that you're continuously linked to the sensory surface, even in discrete motor act like that. But there's a delay. So it's not like there are only certain times when you're open to updating. I have another more sophisticated example, but I'll skip that now. Now, if you have an activation variable that is a real number, so it's a continuous variable, and if it evolves continuously in time, then the only way to talk about its evolution in time is through dynamic systems or differential equations. I used to derive that from recurrent networks, but it's actually a pseudo derivation, so I dropped that. When I'm saying the only way, by that I mean that is the mathematical formalization that is known in our current understanding of mathematics, of how that works. That's how we describe time courses of continuous time variables. And there aren't really any real alternatives. There are some seeming alternatives that would, if you just were to write the time-varying function, there's some in mathematics called non-autonomous, but that is actually not really a solution. That is just hiding the dynamical system. Mathematicians would just consider time then to be a variable of the dynamical system. It's also just a dynamical system. The thing that you might have seen in recurrent neural networks is some kind of recursive rule in which the new activation is a function of the old activation. I can maybe make that point on the whiteboard just to make sure that we exclude that. For instance, if you have a feed-forward neural network, you would say, well, the neural network is just a function where the output is a function of the input. Right? And that's very easy to compute. You just put an input time course, let's say, and you get an output time course. But if the net is recurrent, the problem is that some of the input will come from the output. That is what recurrency means, right? If you have a network like this, let's say, onto this neuron and then onto that neuron, then this neuron gets input from here, but the input depends on its own output. And then you can't really understand that. And then the way of how people deal with that is they say there is a time index, so this is the output at time e, while what I'm using as input is at the earlier time I minus 1. So that depends on the output that I had at time I minus 1. And I have a discrete time, and this is sort of an iterative law then in time how I do that. And a lot of these connections neural network simulators offer you recursive rules like that. And those recursive rules are actually just dynamical systems. Mathematically speaking, this is a discrete time dynamical system. And the discrete time in this case is particularly odd because it's synchronous. That is, all the neurons get updated at the same time. There's some kind of updating cycle in the network. That is clearly just metaphorical. That is not real in the brain. If you go to continuous time, so you essentially think of spiking as some asynchronous sampling of this, end up with a continuous time formulation, and then that's what you have up there. Right? And that's why I'm emphasizing that that is the only thing. So what we have to figure out is what function f characterizes neurons. And that's the argument that I will have to make now. And that's a little bit hard for those who don't know anything about dynamical systems, but I think in this audience, pretty much all of you know what a differential equation is, right? Who has very limited familiarity with that? Anyone? You had a whole summer school about that, and you also. So take me aside. Maybe if you have trouble, it's a little hard if you don't know the solutions of differential equations. And now I'm saying, given the solutions, I want to find out the equation. It's a little more complicated. So I'm trying to find out qualities of the equation. I will end up claiming it is something like this. It has a negative slope here. And that is actually odd. Nobody in neural networks actually talks about that. It's often a mystery term where suddenly somewhere later in the paper you see a minus u term, which makes this negative straight line. And I'll argue now why that is really essential. So let's think of the simplest function we could have, no function, so f equals 0, right? I'll make a point about that, we always have to think of the system in response to noise. We know there's sensory noise, we know that neurons themselves are noisy, and there's also a more abstract way of thinking about noise. The nervous system very, very densely interconnected. Typical cortical neurons have 10,000 inputs, not these 5 that you see on the plots of connectionist networks. And another number, the average number of synapses you need to get from any neuron to any neuron in the brain is about 5. So in that sense, they're densely connected. There's some other sense in which it's sparse, but that's not directly relevant. So if that's true, then it's also true that a lot of these connections are not relevant for any particular task. Now, you might get a vestibular input to your visual cortex, but in many cases that is not really currently active. And what that means is that any spikes that come in from the input that you're currently working on is essentially noise, a perturbation. And in order for your neural function to be realized, you have to be stable against that kind of perturbation. Very intuitively, daily life example, we're all attending to objects, making a saccadic eye movement to it, foveating, and bring it into the perceptual foreground. But we have, of course, all these distractors. And so just the fact alone that we can focus our attention for a moment on one particular object in the visual array is already evidence for this capacity to not be distracted by noise or distractors. And so that's what I'm using in this argument, that we should consider noise and then it should have properties of these neural dynamics that they can deal with that. And so here's the mathematical formalization of a system that has no systematic dynamics. F is 0, but noise, the zeta here stands for, or this is supposed to be xi, I guess, stands for a Gaussian white noise process. That will be the only admissible kind of noise. It will be independent at every moment in time. That's what the white expresses. So it's a new kick every moment in time. That's pure noise, no correlation in there. If there was some correlation, F wouldn't be 0, because then that would be captured by the dynamics. That it's Gaussian is, as you may know, central limit theorem is a general assumption about a lot of different sources for causing the noise, and then generically it's Gaussian. So I'm trying to plot that here on the right-hand side in terms of this Gaussian probability distribution, and it's supposed to stand out in the third dimension, right? So for every u value, you have a probability distribution for the rate of change that is centered on 0 and is some Gaussian. And it doesn't depend on you. That's why for every value for you, you would have the same Gaussian distribution. Significant thing already in neural dynamics, noise is a contribution to the rate of change, not directly to activation. You can't set activation directly. If it's a dynamical system, you can only set its rate of change, and it will then change, because activation will be continuous. It will not jump around. So what I'm trying to make intuitive here is that if you have a situation like that, any of these levels of activation are equal. If you have any of these activation levels, then on average your rate of change is 0. So on average you're going to stay there. But if noise pushed you, let's say, from the resting level to this blue one, there's also no reason why you would go back. You just stay there then. And that shows up as here as this diffusion. Here I simulated that equation on a computer, starting it all at the same level, the resting level. I just took some negative number, called that resting level. And then I just integrated that in time. And as you see, there are 5 traces here, I think, or 6, 5. And as you see, over time, they diverge. There is more and more uncertainty about the level of activation in the presence of noise. This is what you know as Brownian motion. This is another mathematical manifestation of Brownian motion, also sometimes called diffusion. And it's intuitive why that happens, and it's bad, right? If that happens, that means that your neural dynamics is not resistant to noise. So why it happens, imagine that you got a couple of these random kicks that put you here. Now from now on, it's just as likely that there are kicks that push you further away as it is that you get back. So on average, you're not going to go back, certainly. I mean, you just do anything. And similar if you ended up somewhere else. So over time, there are more chances to gain some distance from the initial value, and there is no mechanism to get you back. And that's why over time uncertainty grows. So Einstein famously proved that the variance of a process like that increases in time. It could increase with the square root, or depending, it actually depends on the dimensionality, depends on some things. So you can actually analyze that in this very general form, and the modern field of these stochastic equations is actually structured by that. And so that will be not a good candidate. So what we actually need is a dynamics that limits that growth of the uncertainty. And to limit that will mean that when we are already at a high level of activation, that then the probability distribution is not centered on 0, but centered on some negative rate of change. So that now it is more likely, if you already had a large value, that you now get a kick toward lower levels than toward higher levels. That will be a way of limiting that diffusion. And of course, analogously, at very low level of activation, you have a positive rate of change. So I've drawn that with that straight line, and that's supposed to be the mean. It doesn't have to be a straight line, just any negative monotonic function that would describe, let's say, the mean around which this distribution is centered. And that will be then sufficient to limit that growth of uncertainty. And there you see the minus u term, right? This is now no longer purely stochastic. This is now a statement about the mean of the distribution, so it's part of the dynamics. I therefore keep the purely random Gaussian white noise and write the rest down as a part of the equation. I have this minus u term there on the left that is really stabilizing the activation. Yes?
So the minus u term, is it reading from the previous time scale or average of whatever you have read?
So this is now, I suppressed the index, so this is the activation at time t. And on the left you have the rate of change of time t. So in continuous time, you don't distinguish between past and present because it's only infinitesimal. And therefore, there's only one time in there, the present time. And in fact, dynamical systems have this notion that the present determines the future. So you don't need to talk about the past anymore. And in stochastic processes, the analogous thing is the Markov property. This is the continuous time Markov property, which mathematicians call diffusion process. Just to confuse us, it's sort of like the physical thing, but it's just a mathematical term. I added this h. This is the thing I announced. We have an h here just to make sure that the zero crossing of that straight line is at a negative level that we will then call resting level. So because by convention, we say neurons that have not received input or when nothing significant has happened will not impact downstream neurons, and so they should have negative level of activation. And this H is therefore a negative number, so it's plus H, but it's minus a number actually. So that's the little confusion that we all use this constant that has a negative value. It's not a big confusion, right? You can easily figure that out. So you can see the zero crossing is where u dot is 0. So you put u to the other side, so u would be equal to h. So the resting level is where u is equal to h. The white noise process would have a mean of 0. So that's the stabilization term. It is the only term on the right-hand side of the equation where the u is not first sent through the sigmoid. All right, there's a minus u that really changes sign. So you can see that minus u is not part of a neural network kind of description. You know, in the neural network, there are only things here that go through sigmoids, because that's what the synapses do. This is not, doesn't come from a synapse. It's actually the intrinsic dynamics of every neuron. There's sort of a seductive analogy, because if you look at membranes, the membranes are governed by an equation like that, which you can see from the fact that, I think I have that in a moment here. Yeah, I can use the slides here. So the solutions of these kind of equations are exponential functions. I'll come to that. And membranes actually have these kind of exponential relaxations. If any of you ever saw these intracellular recordings where you inject a current into a cell, put an electrode through the membrane, and you can inject a current, then you will get this relaxation to a new level, and it's exponential. And that essentially proves that they have this kind of dynamics. But it's a superficial analogy, because the time scale at which membranes do that is at least 10 up to 100 times faster than that of populations. Typically maybe 20 times faster than that of populations. There is an argument to understand that. Actually, Thomas Trappenberg in his book reviews that argument. There's recently some real mathematics about that. Generally, the connection is not so clear, but it is not, at least not a straightforward thing of how you take the biophysics of a membrane and then derive this equation from it. So in that sense, it's a phenomenological equation we're currently looking at that I will later claim is the dynamics of populations of neurons. Okay, all the other terms in that equation we'll get later, and they have sigmoids. We'll look at self-excitation and coupling and so on. They have sigmoids. Now, I wanted to spend just a few minutes on this equation and just reintroduce the terms that are used under behavioral dynamics already to make sure that you know what an attractor is and stability is and so on. And there's one new point about that that I just already flashed, the notion of time scale. A very important notion we all use, but often misunderstood. So here I formalize what a dynamical system is. Dynamical system, here as a differential equation, has this fundamental property running under the label of existence and uniqueness theorem in mathematics, that given some initial level of activation at some initial time, 0 in this case, the future from that point of time is uniquely determined, is a unique future from the present. The theorem is true if the function f is smooth enough. This one would certainly be smooth. There's some variance of this theorem for different amounts of smoothness. Sometimes we violate that a little bit by making step functions, but this is very mild, and you could always smooth it a little bit and would be true. In mathematics, it's also only locally true. It's not true that time can go to infinity, but in practice, it's never really a concern. For mathematicians, this is actually the defining property of dynamical systems, and you can prove it for differential equations. And they have some funny way of talking about dynamical systems in more abstract ways. For those who know this as invertible diffeomorphisms, some of you might have heard that. No? Okay, forget about it. So this is it's actually an interesting field, but it's a more abstract theme. There's some reason why we actually are interested in these more abstract versions. Very pragmatically here, I introduced the dot already on the U. That's the rate of change. That's how physicists talk about rate of change. Newton invented that. Mathematicians sometimes use this, du by dt. It's also just a symbol. It's not d times u and d times t or anything. It's just a symbol. I find it really awkward, but mathematicians like it somehow. Leibniz invented that one. He was more a mathematician. So I'm primarily using this here. And the dot is always when the derivative is with respect to time, while this you can use when your derivative is with respect to something else, for instance, space or some other thing like that. So I will be always using this, but if you see that here I sometimes do that because there's no dot in that font on the program, so it's a little awkward. And now I have managed a way to put a dot on the EU by graphics, and later plots you will see that. Okay. Here I'm, I explained that before, this is the resting level. These little arrows are another way of representing the dynamics. So at every level of U, I can use a little vector that points in the direction of change, and the length of the vector is the speed of change, the amount of change. So you see, this translates into that arrow. The direction is toward this fixed point, to the right, and the length is a function of that. So here, this one is longer than that one. This is actually mathematically deep. This is called a vector field because U spans the field, and for every value of U, you have an object of the same dimension. In this case, it's just a signed number, U dot. And that generalizes actually if you have many neurons, a high dimensional vector of neurons, then you can say the dynamics of the neuron is a vector field that is for every vector of neural activities, you will have a vector that points in this direction of rate of change. And I'll show you a two-dimensional example toward the end of this lecture. And in fact, instead of differential equations, mathematicians talk about vector fields as setting up the differential equation. So it's just connect to jargon that you will be seeing in our papers. Then I previously said what a fixed point is. It's the fixed point is the intersection of this dynamics with the u-axis where the rate of change is 0. That is actually a solution of the differential equation. It's a constant solution, stationary solution. That it's a solution of the differential equation is obvious from the fact that this side is 0 there. So this side is 0. And the solution is constant, meaning it will actually stay 0. And so, both sides of the equation are the same, 0 equals 0, and so it's a solution. It's a constant solution of the differential equation. So fixed points are stationary states. This fixed point is stable, and by stable I mean that nearby solutions converge in time to the fixed point. Converge in time mathematically defined, infinite time, the difference becomes smaller than any bound. There's some kind of mathematical definition of that. From high school, you hopefully remember that. And nearby, mathematicians talk about infinitesimal, so for any precision, you can give an interval that you're smaller than that. But intuitive means that if you're somewhere near that fixed point, you will converge to it. And how far that range of attraction extends is a separate question. That doesn't matter for the stability. This is what mathematicians call asymptotically stable. And like engineers and physicists, we loosely use the term stable for that. Stable is actually a little bit different, and I don't formalize it here on these slides. Stable just means if you start nearby, you stay nearby, but you don't have to converge. In physics plays a big role because that in physics energy is conserved, and energy conservation actually makes it impossible to have attractors. Anyone interested in that can ask me about that. And so there's a whole class of systems for which asymptotic stability doesn't matter, isn't relevant. For us, that stability concept is relevant because unstable is the logical opposite of stable and not of asymptotically stable. So unstable means there are some initial conditions close by from which you don't stay close, from which you move away from the attractor. That's unstable. And I showed you a repeller. A repeller is like the optimal unstable thing where you move away from in any direction. If you're just a little bit away from the fixed point, you always move away. But there can be systems that are less unstable. There's just some special values arbitrarily close from which you diverge, but there are other ones from which you stay around, and that will be sufficient for being unstable. And you will see systems like that. A saddle point is an example of that nature. So we mathematically, strictly speaking, need that distinction, because if we were just say something is not asymptotically stable, it could mean it doesn't converge, but it stays close. But that's not enough. In these lectures, I'm not formalizing this more. This is the sort of mathematics that you have to go through to make all of this rigorous. Now, this is the one new point compared to the behavioral dynamics. Now, the mathematics is, of course, the same. The one I discussed this morning, and now it's the same concepts applied to different kinds of variables. Now, I didn't emphasize this morning this property of linear dynamics, and I'm doing this now because timescale is such a pervasive concept. So if you have a linear dynamical system, you get an exponential solution. Actually, I drew this by hand. It's not quite perfect, as you see, but it's supposed to be an exponential. Many of you will know that, right? The engineers all, of course, know that. For whom is this somewhat new? Everyone knows this. For the psychologists, good. I derive it just to demystify it. So u dot equals u. Let me make a simpler equation, just for the exercise. The solution is exponential of time, and the reason for that is that the derivative of the exponential reproduces itself, so it's just the same, right? And therefore you see immediately that it's the same, right? If I put some coefficient here, the coefficient comes up here because when I take the derivative, the chain rule, the inner derivative comes in front, so you see that's the solution. If alpha is negative, then we're right here, right? So I can make it explicit, then we're right here. Okay, so it's a mathematical triviality in some sense that that's true. You could say the exponentials are exactly the solutions of linear differential equations and vice versa. That is actually very true. When you go to higher dimensions, multiple systems, it's also kind of true. There's some complications about it, running under the Jordan normal form. Some of you might know that. You can have degenerate directions where the solution is not exponential, but t times exponentials and so on. But roughly speaking, so if you allow for vector-valued exponentials, exponential of a matrix, then it's also true. Why is that important? It's important because only exponentials, the only time function, really have a scale. And by scale, I mean that I can say how much this is changing in time, irrespective of the units, irrespective of knowing how far I am from the asymptotic value. For instance, here I have some starting value, and then I'm looking at the time tau, after which the starting value has to decay to the starting value divided by e, the natural number, so 2.7 something, the base of the exponential. It's about 3. Let's say it has decayed to 1/3. This was done again by hand. I'm not even sure this is actually true. No, it's not. But no. Qualitatively, that's true. So after this time, it has decayed to 1/3. And that's independent of that starting level u of 0. So for instance, if you now look how long it takes this to decay to 1/3, then it takes the same time. Right? So you don't actually need to know about the units of the system. And that is the only way to talk about a time scale that characterizes the process or the time function per se. If you have some other time decay, for instance, if I can plot just many other kinds of functions, for instance, 1 over t or 1 over t squared or 1 over t, the square root of t, they will look sort of the same if I plot them. But there, the rate of change depends on how far you are from the asymptotic value. So there you can't say how fast they will change independent of knowing a particular value where you are. It's only true for the exponential function. And if you think about that, it's actually already here sort of in that formulation, because what this actually says is that the rate of change divided by the current level is a constant, in this case a negative constant. Now that means that the change in percent of the current state is the same. So that's the concept that implicitly we're using all the time. So for instance, when you look at these timescale books where you see the universe and atoms and then humans somewhere in the middle, and so you go from 10 to the minus, from Planck time to the age of the universe. You know that? There's a book like that, it's really fun. they talk about different time scales. That actually really makes sense only if at every scale we're talking about exponential processes. If you're not, then then it's a question of what you're measuring. Humans have something that happens on the time scale of 100 milliseconds, and then something happens on the time scale of years, like aging. And so it's a question of what it is that we're talking about. Now, it turns out that almost everything is exponential in some sense. And that is, you will see this a little bit later, that is ultimately because stability is pervasive. Almost all processes in nature have some stability properties. If not, or at least the things that we care about are like that, because the things that we care about are reproducible, and that means they are somewhat resistant to noise. And therefore they are asymptotic around some stable state. And when something is around a stable state, even though it might be, the dynamics might be more complex than that, for instance, nonlinear in the sense, for instance, going like this, or maybe some funny function. But if I narrow in around the fixed point, around the attractor state, and look closely enough, at some point it's a smooth function. I can approximate it by the linear function, and then I get the exponential process. So it's very generic. This runs under the label Hartmann-Grobman theorem in mathematics, for those who care about that. Which essentially says linearization is a good thing. So actually in physics, in the disciplines where the mathematization through dynamical systems is very well known, very common, people use this actually in the opposite direction of saying it's hard to get something non-exponential, and you have to do special things. For instance, power laws are hard to get in some sense, because the power law violates this exponential relationship, so you have to do something special to get it. And that can truly be said. So for us, this means that we're fine talking about different scales if we have underlying dynamics. That will be relevant for learning, where we will have a learning dynamics, and that has a different slope from the behavioral dynamics, and then we can talk about their scales and really compare them. Or adaptation, or different kinds of behaviors at different scales. It will be much less obvious when we're talking about, for instance, some time-varying environment that changes in some way that cannot be characterized by dynamics. Now we can't really say what the scale of that is. Then it depends on the units, on really understanding, how much does a change of 5 lumen, let's say in light, how much change is that? Only then can I talk about it. Okay. This was for clarification. This argument with timescales we'll be using all the time, and we're referring to it in this sense. And it is always the coefficient in the equation where sometimes, essentially the slope, this here is the slope of the dynamical system. And so this is a very fast and this is a very slow system. Right? And so we're talking about that coefficient. Sometimes we put the coefficient here on this side, and we're saying tau equals u dot. Tau times u dot is minus u. Can you see that? So it's just dividing by that, and that's then like a rescaling of time. All of time is measured in units of tau. Yeah, roughly speaking. Okay, that's the one new point I wanted to make about dynamics. Instead of a simulation, I just argue, I already said verbally that starting from different initial conditions, you always go to the solution. And the point about that is that if you know the stable fixed point, that's the attractor. So we just use that word attractor for stable fixed point. Then you actually know something about the entire ensemble of solutions within the basin of attraction, which I've glossed over so far. But within a certain range, you will know that all solutions will converge there. That gives you sort of a survey over all the possible solutions. And that's how we will use our design principles. When we want a particular solution to arise, then what we really want to say is we want all transients to relax to this state. And that's essentially brought about by putting the attractor at the right spot. Later we'll see how we, for bistable systems, how we also design the boundaries between different such conversion zones. Good. So this was all just one neurodynamics. Now let's think about input to the system. So this system so far didn't have any input, only resting level. Inputs are now just contributions to the rate of change, additive in the first approximation, usually with a sign. If the sign is positive, we call that excitatory input. If the sign is negative, we call it inhibitory input. In the nervous system, that's different. Neurons only have one kind of synapse that's either positive or negative in effect in terms of the postsynaptic potential. Neurons are excitatory or inhibitory in terms of their effect on the downstream neurons. They can only do one of the two things, and therefore there's a clear signature for that. We don't mix the synapse signs usually. So what that means is that when you have an input to your neurodynamics here on the top line, the thin line was the dynamics we just looked at without any input. If we add an input, that means now we shift the whole dynamics up. You know, this is an input that's independent of the activation of that particular neuron. That's generic, right? In the nervous system, the input is just something arriving on the dendritic tree. It's not informed about whether this neuron spikes or not. It just has the same action independent, the same effect independent of the current state of the neural network. And therefore, this does not depend on you, so it shifts the whole line upwards. As you see, what happens is that the attractor then shifts to the right, in this case for excitatory input. As you lift the line up, shifts to the right. If I, here I did the tau on the left. If everything was right, you see the new fixed point is u. Put that to that side. U equals h plus u, and that's what I call it s up there, the input. That's what happens. Shifts it to that new value. So what makes that your dynamical system then actually goes to that new attractor is the minus u term. Right? If you're sitting at the resting level, you shift the dynamics up. Now you no longer have a fixed point there. Now you have a positive rate of change. So it's actually the destabilization term that moves you to the new attractor. We could also say it allows you to track the attractor. If you think of the attractor moving continuously in time, you're tracking it. So here's an example. Here the input was 0. I was sitting at resting level. I make a jump change in the input. And the system, you see here's a non-differentiable term, so we shouldn't have made it quite so rough. The jump could be smoothed a little bit, but that's not a big problem. So you get a little edgy, and then it relaxes exponentially to the new value that is specified by that input. It's essentially the input plus h. Remember, h is a negative number, so shifted a little bit downward. G of u is plotted here. G of u is the sigmoid applied to that activation, and that is, of course, what will ultimately be transmitted to other neurons. And you see that that comes up from 0 a little later, namely just around where this crosses 0. You see, it starts a little bit early because the sigmoid is not a step function, so it's a little. It always starts when u is about here. There's a range here of that sigmoid, and then it's about here, and then it saturates. In this case, to the constant value. That saturation doesn't have to be so strict. So in these equations, you can have many inputs. Typically, you have maybe a lot of inputs from different sources. There will be all these different terms. That's the sum that you see in connections networks over all inputs. What you don't see have in connection networks is this. This you sometimes have it as a bias term, where you set the default value of the neuron. But this you don't have, right? And this is what you need to do the time continuous version of it.
Excuse me, what was the G of u?
So the G is the letter I used for the sigmoid. So this is this function here.
Okay.
Yeah? Recognize that? Okay. Okay. I assume that this is somewhat familiar to most of you, right? At least bring it to the foreground. I'm going pretty quickly here. Other questions? I'll start a simulator. It's kind of trivial so far, but just wanted to familiarize you with that. This one here. So this is the simulator that that is part of this package. Sebastian Schneegans hasn't presented that yet. Tomorrow you will have a whole session about these simulators. This is the odd one. It's for discrete neurons. It has actually 2 neurons. And you will have a chance to play with that tomorrow afternoon and with much more advanced simulators later. I just use this opportunity to introduce that notion. You have sliders here for the parameter values, and then these windows actually show you the solutions in over time. Right now you don't see anything because both systems are in the fixed point. This is neuron number 1 on top, neuron number 2. This is a time course. So actually the time, this is running in time, you'll see that in a moment. And so this moves with the solution, so you're always seeing at 0 is the present. Currently it's at -5, and this one also at -5, because the dynamics is u dot against u. Here's 0, you know, so, sorry, here's 0. The axes aren't put in here, so the intersection is at -5. That's this h parameter here, -5. And it has some slope that you can also control. By clicking advanced, you could get access to the other parameters like tau, and you can make it, give it different slopes. And this neuron up there has the same dynamics. Right now they're uncoupled and they're just 2 copies. I'll just use one of the 2. And I can give input to this. As you see, as I shift the slider up, you see that the function shifts upwards, as you just see now. Fixed point moves here to the right, and you saw that there's exponential relaxation to the right. The curve in that funny color, whatever that reddish color is, that is always the input plus the resting level. Here, input and resting level are sort of have the same function, really, so we can't really say how much of it is input or resting level. Later, it will play a different role when we have our fields. And so that tells you, in a sense, the target attractor that you would have if everything else was the same. Just show that again, relaxes here. And if you want to play with that, you can, this is in the package, so you'll have all of that on your computer tomorrow. You can go in there and look at the tau, and you can actually make it steeper and less steep and see all the different things that can happen. In this simulator, like all the simulators we're using, we're actually not making it possible to set the initial condition and then relax, which is maybe the... We always say relax for the movement to the attractor. It's just jargon for that. I don't know whether... Physics, I think, where they say relax by going to the attractor. Because you're not relaxed when you're not in an attractor. Very true for dynamical systems. So it's just jargon. Excuse me, I can't resist using that jargon. So we're not actually allowing you to manipulate the initial conditions. In a sense, that is not by chance, because if we're looking at a system that's autonomous in the world, or we're looking at a nervous system, it's actually never true that we can set the initial condition. The only way we can set the initial condition is to manipulate the environment, for instance, the history of stimulation, such that we maneuver the system into a certain state. And that's how you do that here. That is, you set the initial condition for one experiment that you want to do by giving it a history that it was, for instance, in the activated state. And then it will, you know, now I can change something from that state. In this case, maybe just remove input. And then I can study that dynamics with that initial condition. That's sort of a general philosophy about how we use dynamic systems, and that's actually quite appropriate, because that's also how organisms and robots work. That will play a much bigger role when we use fields. Now, this is very boring, and before it becomes exciting, we have to do one step in the lecture, and I think I'm doing it at a good rate, so we'll be managing. That is, we have to introduce a real neural network, not just one neuron that gets input. So the simplest neural network is one neuron, right? And it's a network because there's some connection, a loop. This is the self-excitation. This does actually exist in the nervous system. Later you will see that this is actually a representation of a whole population that self-excites, and then it doesn't have to be an individual neuron exciting itself, it can excite its neighbors. But there are things like that in the nervous system. Actually, general rule is if you come up with something, some nervous system somewhere has it. So it's actually not very constraining in terms of what kind of connectivities exist. There is also in the nervous system shunting. I just mentioned that. Shunting is when the input depends on the activation state of the neuron. This is by one synapse sitting on top of another synapse, in a sense, and then it can veto the effect of one synapse. And that is a arrangement through which inputs are not additive. But we're not touching that. It plays a role in some special cases, but not, it's not part of our main language. So this is all additive. This is fancy drawing, simple drawing. It's just the same thing. I just thought this was fancier somehow. It has words rather than labels here. So this is the equation, all familiar. The only new term is a new sort of form of input. Now this is the external input that comes from the outside, from a stimulus. Might be a time-varying function. I called input before, now I call it S. And now here is the self-excitation. This is an input that depends on you. It's from that same neuron U. And here I use sigma. Unfortunately, sorry, I forgot to change that. We changed the notation. Sigma used to be the sigmoid, and now we call it G. And on this slide, I still haven't corrected that. Really need to do that. Oh, I forgot my piece of. Oh, here it is. I can take that note so that I correct that in the future. It's not instantaneous because I have to go through the typesetting machine. So sigma of u should be really G of u in this slide. So this is the same function G of u. This is a constant in front of that that says how strong that synapse is, how strong that self-excitation is. We'll look at that in a moment. So what does that do? We can first just try to sort of mentally assemble that. We have the minus u function, and on top of that we have one of those sigmoids. I don't know how steep that really was. This is actually an actual function. And so if you have that straight line and you add a function like that, what will happen is that you have, from here on, you have again the minus u function. If you're up here, you have the minus u function shifted by this amount. Shifted up by this amount. I'm not sure the scales are the same, if it's exactly that sort of shift. And in the middle, you have some transition between those two. Right? That's just what this function looks like. If I make this steeper here, then this transition regime would be sharper. In the extreme case, it would be almost a jump upwards. See, this is a nonlinear function. So far, nothing has happened. It still has that resting level fixed point. The fact that there's some stuff here on the right doesn't really matter so far, but I can quickly get it to matter if I add another input, add a constant input. The different lines are supposed to reflect different amounts of input. So I'm starting with this one and then adding different inputs. And you see something here happens on the right. The green ones are always attractors. These are repellers. So a new attractor appears here on the right. And specifically, as I lift this up, this attractor is just shifting, still fine. But at some point, this starts to touch here. This is where a bifurcation occurs. It's a tangent bifurcation, where an attractor and repeller appear out of nowhere. There's a repeller here, positive slope, an attractor here. If I go just a little bit above that, you will have these two kinds of fixed points. And then as I shift further, the attractor moves further to the right. The repeller actually moves here to the left, and you can see that there the complementary, or the sort of complement of that bifurcation occurs, where now the repeller collides with this attractor, and they lift off, and it disappears here. Actually, only when that happens would your system actually switch to the new attractor. Right? It would be following that attractor right up until this point, and then it would switch here. Then the interesting feature will be that if you now lower input, it will actually track this attractor until it disappears here and switch back. It will switch back actually at lower levels of input than it switched first up. That would be a form of hysteresis, where the response of your neuron would depend on the direction in which input changes. If input increases, you switch at higher levels of activation than if input decreases. And I'll just elaborate on that in the next few minutes. So in the middle of that, we have that bistable regime, right? Just as I showed on that previous slide. So that will be a regime where your activation that's realized in the long term is not uniquely determined by the input. The input just sets up that dynamics. Which of these states you observe depends on your history, in this case, your inner state. If you previously had a low level of activation, you would stay there. And that's what I hinted at with the hysteresis. Or if you had previously a high level of activation, you would stay here. If you previously were exactly at 0, then again, fluctuations would decide the story for you. So this is sort of showing you that a simplest neurodynamics with the self-excitation is now no longer really input-driven, no longer uniquely determined by input. So it's no longer an input-output function. Its output depends on its own inner state. Right? That's where it's really qualitatively different. Very, very simple, but it already does that. Now, this is the same slide as before, just with different text. We call this instability here the detection instability. This one, the reverse detection instability. And this is this notion that this neuron stands for its input. If it has a positive level of activation that through the sigmoid will be transmitted, then that is the decision that there is significant input for that neuron, has detected that input. And so this instability is where the neuron switches from non-detection to detection. So it actually turns out it's a discrete transition. It will really make a rapid change in activation. We'll look at that in simulation at that point. And if input decreases, then the switch, where this instability happens will be the switch where you go from having detected to no longer detecting. That's reverse detection, or losing the detection. It happens at lower levels of input, and that means that once you do a detection, you're actually self-stabilizing that detection. You need less evidence to continue to detect the state than you need to initially get the detection. And that is an important property of neurodynamics. Tomorrow morning in the field session, I'll show you what work that does on a robot. Just narrowing in on that, I just amplified that and just look at this local section. The bifurcations are local, and here's an attractor repeller, and then you lift that up. They are tangential, so the slope is 0. See, I said the slope is the degree of stability. If it's very flat, it's very slow, and so it becomes infinitely slow right at the bifurcation, and then there's no longer a fixed point. If I plot the fixed points and their stability as a function of stimulus strength, then for low stimulus strength, I have these two states, the stable and the unstable, and they collide. If you figure that out, it's like a square root of stimulus strength. They collide like that and, in a sense, annihilate, and then you have no more fixed point. This is called a tangent bifurcation. See, this is just tangent here as it lifts off. This is the most generic bifurcation. That is, no other constraints have to be true for this to happen. The only constraint is that you are at the bifurcation. This exact same bifurcation. Yep.
Is this biologically possible? Because by adding inputs, we are changing the resting level.
It is definitely plausible. I don't think I understand your argument. The resting level is always there, right? I just, you mean calling these different things resting level? That's not right. And the resting level would be just one, and then it's being shifted by input. So when you have input, yeah, right? So maybe I should delete that. That's misleading here. So at the other bifurcation, actually, I just discussed the reverse detection instability. Now, the other one is just sort of the same thing, everything upside down. And that's against, it's the same thing. If you let time run backwards, that means the t up there changes sign, then everything flips. And here also things flip. But other than that, it's the same, right? It just means that high stimulus strength, you have these two attractors. Low, you don't. And other than that, it's the same logic, right? So I don't have to elaborate on that. So just show you the bifurcation comes in two shapes. And this is just to illustrate that hysteresis. That is, if you have a time function of input that shifts your attractors, so you're seeing initially here in the wood, that attractor is is moving, right? The green line here is moving here to the right, and that movement to the right then shows up as this movement, and then at the critical point you will have a much more rapid change. It's not instantaneous because it still takes some time to relax to the new attractor. And then if you start the reverse movement, now you're moving the input down, then you will switch at a later state. That's how you operationally we see hysteresis. We actually did, I don't seem to have that here. We did psychophysics to really study hysteresis like that. You might know that hysteresis is very common in psychophysical detection experiments, but it's usually considered to be an artifact of the procedure. For instance, if you you get some funny limit stimuli where you hardly see anything, then you might have what is called response bias. That is, if you say no once, then you keep saying no until you get some good signal, and if you say yes once, then the threshold for you to say the same thing again is less. But there's actually there's a way to minimize that kind of factor and to make sure that you have actual perceptual hysteresis. One thing is that the perceptual alternatives are very clear, so you don't have a vague, fuzzy threshold stimulus. And another is that you systematically study the effect of the response mode. So you can ask, for instance, people only to make a response once in a whole sequence of stimuli that is after the transition, and then look at how the response probability varies with the direction in which you go through the instability and so on. So we made a whole research enterprise in nailing down the perceptual nature of hysteresis, and it is there. But I'm glossing over that in this talk. I would just like to simulate which one is it here? Simulate that self-stabilization. So I have a slider here for self-excitation. That's the CUU connection strength of U onto U. And by increasing that to maybe this, I see around 0 I have added a sigmoid, and you see the relatively sharp sigmoid. That's why the transition is like that. You could vary the strength again by going here. For instance, just for fun, I'll make it sharper. You see how it's sharper, and maybe I'll go back to make it less sharp. 5 is a good number. Oops. And so far nothing happened because the resting state is still below 0, and then I can make something happen by shifting this up. I'm just giving some input, right? Shifting this up. You see now there's a new attractor here. This mark actually marks 0 crossings, but I'm still in the off state, so I have to get to the detection instability that will occur when this here goes through 0, right? The 0 axis is here. So I'll go here. Right, now I have a little noise here on this, so it might actually be able to go switch pretty soon. Not yet. No. Oh, noise is off, that's why. Okay, now it switches. So you can certainly see here how the switch is so much faster than the tracking before, right? And so now it will stay there, even though I lower input. It is in the on state, right? Until I have the reverse detection instability somewhere here. Maybe here. And there it runs to the offset, right? That will be your hysteresis. Now I'm getting the switch at a much lower level of input 1.2 than I needed to get it first going, which was probably, what was it here, like 4.1 or so. That's hysteresis, if you can read those numbers. Of course, in reality, typically you have some noise. I have a button here to add noise. You see some noise, and if you have noise, first of all, the stabilization is of course important. Let me restart here from 0. But then it also makes, noise is good in this bistable regime, stabilizes you against switching. No, it challenges the stabilization. Oops, this is too much. I go to, oops, sorry, I moved too fast. Let's go back. Okay, really go back. Yeah. And now what I wanted to demonstrate is that with noise I get I can get the switch before it really becomes unstable. Like from here it might spontaneously switch after some time if I'm lucky. Maybe it's still, maybe let's make noise larger. Yeah, that didn't quite happen yet.
Sure.
Yeah. No, yeah. It has to be studied a little bit more carefully for that, but it certainly stays then put in the new shape, right? So it's important to stabilize decisions against noise. And with noise, the instabilities tend to happen a little earlier, or the switch tends to happen a little earlier. I wasn't really able to reproduce it. So it's something you can play with. You see on the right now, the resting level plus input is no longer tracked by the solution. The solution is really a finite distance from the state, from the input. And that's the self-excitation that does that. Right? Good. Last topic of this day is going to, I know you're running on extra reserve perhaps now, is a neural network with two neurons, 1, 2. And a different kind of coupling. If I just couple two neurons excitorially, then the same sort of thing happened as self-excitation. You can imagine two neurons that are mutually excitatory will have the same net effect. So nothing new happens there. But now we have a chance of doing inhibitory coupling on the two neurons. So this neuron inhibits that, and that neuron inhibits this, and this shows up here in this equation. I have now an index to these neurons, neuron number 1, number 2, same equation. And now neuron number 2 shows up in the equation of neuron number 1 with the sigmoid, again, sorry, the wrong letter here, with a minus now. I should have put a constant here. We have constant in the program. And here it shows up, neuron number 1 shows up with a minus in the equation for neuron number 2. And I have some inputs on the right-hand side as well. Right, that's clear to everyone? So to discuss what happens, I can take two figures. I just want to clarify. We call that mutual inhibition, and coupling generally in dynamical systems is really just that thing, very trivial thing, that in an equation for one neuron, the other neuron shows up. And if mutual coupling, if that's true for both. That's coupling. That's all that it is. There's a mathematical sense of coupling that is a little bit different. I just mentioned that for the more mathematically skilled people. If you mathematically, you could have that, but there is a way of transforming the equations into diagonal form where they're uncoupled, and then you would say the original system isn't really coupled, it's just a wrong coordinate frame. That is true for a linear differential equation, where you can decouple like that generically, just depending on the structure of your linear matrix. So in that picture, you have to do that transformation to figure out if something is coupled or not. In our system, we don't think like that because the sigmoid doesn't actually enable that kind of diagonalization. And therefore, we just talk about coupling in this naive sense of one showing up in the equation of the other. There is no cheap way of eliminating the coupling by a transformation to diagonal form. Right? Technical parenthesis for those who are from that field. Okay, that's just to clarify the term. And now there are two ways of visualizing that. First, the direct one that we have been using for one neuron is, it's not mathematically rigorous, but we can sort of get an idea for that. And that would be making some kind of mental simulation where we would say, let's assume that neuron number 2 has been activated somehow to a positive level of activation, and then study the dynamics of neuron number 1, and then check if that's consistent with the neuron number 2 doing that. So for instance, if that has happened, then the influence of neuron number 2 on neuron number 1 is this inhibitory coupling, because neuron number 2 is above threshold, sigmoid returns a positive value, that suppresses the dynamics of neuron number 1. Neuron number 1 also gets some input, would have liked to have the attractor on the right is suppressed, and therefore now is again at a negative level if the constants are all chosen appropriately. And if the neuron number 1 is at this suppressed level, its inhibitory influence on neuron number 2 is 0, and therefore it is quite possible that neuron number 2 has that positive value. And that's how we can understand that that state would be a possible state. You could also start with the other assumption that neuron number 1 is activated and then figure out if that was consistent. And if everything is symmetrical, that would be also consistent, and that's how you could figure out the system would be bistable. It has 2 possible solutions. That's sort of a hand-waving form of doing that, and we're actually using that a lot in fields, making this kind of assumption analysis of what kind of peaks are possible. More rigorously mathematical, I'll come to that. A more rigorous mathematical way of doing that is using these vector fields. And I want to take you through that just to enable you to think like that. So here is a vector field representation of the dynamics of 2 neurons. Remember earlier I said that if the rate of change is plotted as a vector field over U, I add to every location in space a vector pointing in the direction of change with length corresponding to the amount of change. And now I can do that for the 2 neurons. I have the same equation. And I do that by plotting one neuron along this axis, the other along that axis. And then I put little vectors in such that this component of the vector is the rate of change of the one neuron, and this component is the rate of change of the other neuron. So here, both of these have this vector field. So the cut through that line gives you exactly that vector field. The cut through that line gives you the same vector field. And in between, it's just the same thing added. So these are actually uncoupled, 2 uncoupled neurons. And it's not, you can't directly visually see that from the vector field. It's certainly a convergent vector field. They will all be, the solutions move along these little vectors, right? The vectors show the rate of change. So the solutions move along these vectors. In fact, mathematically, if it's this is actually linear, so this is all going straight lines. But in other cases we'll have in a moment, the solutions might be curved paths, and the vector is the tangent to the path at every moment. Those of you who know this kind of called differential geometry will remember that if you have a curve in a high-dimensional space that is parameterized, the parameter is time, then the derivative of that of that vector path with respect to the parameter is the tangent vector, and that is the rate of change. It's the vector field. It's tangent to the solution. So you can see the attractor with the naked eye conversion points there. Now, if I add input to both of these equations, the equations of that, then the attractor shifts up there. Now, what does the interaction do to that? So the interaction is mediated by the sigmoid, and we have 2 kinds of contributions. We have that neuron number 1 inhibits neuron number 2. I call this site here because later we'll see in the fields it's actually a whole region, a site in the field. So neuron number 1 inhibits number 2 means that for neuron number 2, there's a contribution that goes down, pushes activation down, negative levels, right? That's along this axis negative. Because of the sigmoid, it only shows up where U1 is positive. So only here do you have an influence of U1. When U1 is deactivated, there's no influence. You see that? This is the same the other way around. So the influence of neuron number 2 on neuron number 1 only exists where U2 is active, and it pushes U1 to negative. If I superpose these 2 things, I get that vector field, right? And so see, that vector field alone would be terrible, because if that was the case, it would go to minus infinity here or minus infinity there. So you need the conversion part, the minus U term, the conversion part to give this any meaning. And this is what would happen. So if I add the conversion field to that, I get this. Why do I get this? Well, here there is nothing to add, so I get the same, right? Here I had a convergent field, and I have a strong field pressing down here. The convergent field is kind of weak, So this one dominates, it all goes down here. It's this mutual inhibition. You don't want to stay where both are activated. Here you have a somewhat convergent field, sort of the same size as this down field, and that makes just the convergent field shifts its attractor down. This is what happens here. And here you have a somewhat convergent field, and this vector field shifts that to the right, so you can also have that here. So you have a bistable system. And by symmetry, it has, if there's an attractor down there, there will have to be one up there. So you get a bistable system. Anywhere to the right of the diagonal, the vectors will actually lead here. And anywhere to the left of the diagonal, the system will lead there. That's the two-dimensional analog of a bistable system. But now the bistability comes from competition, not from self-excitation. If you have a typical starting condition, now remember, initially you have no stimulus, will be in the off state. Now you apply, the stimulus changes the vector field, right? Stimulus is a change of the dynamics. So from this, you apply the stimulus, you get this vector field in the presence of a stimulus. And therefore, you will be initially here, sitting here, right on the boundary. And therefore, it will be by chance whether you go here or there. And that's because this is the symmetrical case where both systems, both neurons have exact same dynamics. More generically, one of these neurons will perhaps get a little bit more activation. For instance, here I gave neuron number 1 more input, so the fixed point is a larger value of U1 than of U2. That's why it's here off to that side. Inhibition doesn't know about input, so it's the same. If I add these two things, I get this kind of vector field. See, this attractor now here to the right has a larger region of attraction than this one. You see pushing it to the right, that this is now a vector field that is more resistant. It's at higher levels of activation than this one. And so what you get is that if I start now with this off stimulus state and apply that stimulus, now I'm much more likely to go here than to go there. Right? In that picture. So I'll show you that in the simulation. In simulation, did I restart this? Yes. I have this button here. CUV is the connection from the bottom neuron is called V to the top. So to make it inhibitory, I have to give this some negative value. And let me think again, how much do I need? I need more than resting level. Yeah, so this is probably pretty good. And the same here, converse units. I want to give that the same value. Fortunately, I was unlucky, and it's a little off. Now, these buttons are a little sensitive here. I want them to be the same. That's too bad. Now it will work because this goes in increments of 2. So -7, both of these. So far you don't see anything changing because they're both in a below 0 state. So no sigmoid, no inhibition. So the only way something will happen is if I start to give an input to one of those neurons here. I give an input, and you see as soon as the activation crossed 0, the sigmoid engaged, it suppressed this neuron, and this neuron is now deeply depressed, maybe also in a psychological sense, totally down here, and this one is nicely up there, not inhibited by that neuron. And if I give an input of 6.5, I can give a little more. I can give, let's say let's take 8. Input of 8. I give this neuron also an input of 8. And still it is depressed. It's suppressed, right? So now I have equivalent inputs, and the initial selection is still correct. The reason why that is the case is that I gave input to the first one first. And in a sense, temporal precedence is translated into competitive advantage. That's the general principle of neural networks. In neural networks, alluding now to your prior knowledge, you know that neural networks, in some sense, the synaptic pattern selects which inputs a neuron reacts more strongly to. So you have an input pattern that matches the synaptic pattern of a particular neuron. That neuron will be driven very effectively by that input, while other neurons that don't have a matching pattern as much will not be as effectively driven. So you can say it's higher input level for that neuron. And higher level really means, in terms of neurodynamics, faster relaxation. Faster relaxation simply because you move the attractor further, and then you have a very high rate of change in your minus u term to go there. I actually can demonstrate that irrespective of the operation I wanted to do here. Yeah, I can do that. Let's just get rid of this neuron. By the way, it switched to the other neuron here, right? And if I can make that point really quickly. If I move that again back, now this neuron stays suppressed, right? So it's actually another form of hysteresis, depends on who was first. Okay, I actually wanted to demonstrate that other aspect, that the when you have a, let's forget about the inhibitory interaction, stabilized, if I make a small change, now this is relatively slow increase. If I make a fast change, a far change, see, the initial rate is much higher than for the slow one. See that? Initial rate. And that's is just a linear phenomenon. It's just because on that dynamic curve, if you're sitting here and you're moving this far, then this is a big rate of change that will make a fast movement. If you're moving it less far, it's less of a rate of change. We know it's an exponential, so the scale is the same, but just the absolute amount of change is different. And therefore, a neuron that is activated a lot will rise a little earlier, a little faster. And therefore, it will have a chance to reach threshold earlier, suppress the other one, and thus the time advantage is translated into a competitive advantage. That's generally true for neural networks. In a lot of neural networks that are not using neurodynamics, the selection is then in readout. Someone looks who arrives at threshold first, and I take this one. But of course, a network like that, the other one would also catch up, and then in the end, they would have the same level, or at least in terms of sigmoid, they would saturate at the same level. What the dynamics does is translate that time advantage into an actual decision. And that decision is then self-stabilized. That is, once one neuron has one, the other one can get even more input. I can, for instance, right now, I can give this neuron, 10 is, of course, the maximum, so that I have on the slider. Let's give it maybe 7. And I can give this neuron more input, like maybe 9, for instance, even 10, I think. It still doesn't win, right? There's a limit to that. If I move further out, I'll show you that for neural fields, then at some point there will be a switch. But overall, the bistability of the competitive dynamics that I've shown you for these two coupled neurons is a form of stabilizing selection decisions. And that's actually something that the fields do as well. Okay, so we're done. I believe I have this is my last slide. So we covered enormous amount of ground. I talked a little bit fast. Be happy to answer questions. Maybe if you have no pressing ones, we can do this in person, or you ask tomorrow morning. Your brain must be almost dead now. So what I'll do tomorrow will not really be different in terms of these basic functions. We'll also have detection and selection. But I'll embed these two neurons in fields. And that really addresses the awkward question that you have so far. How does the neuron know what it stands for? Of course, it has some input, yeah. But is it that for every possible input you have a neuron? This will be sort of the grandmother neuron cell, grandmother neuron concept that each neuron is just responsible for one particular thing. But how do they come in place? this picture of one neuron standing for something specific actually isn't right. One way to establish that is perceptual hysteresis. In perceptual hysteresis, there will be a change to the stimulus, but you will still have a tendency to keep one category of stimulus. So even though it's changing a little bit, so it's not enough to just say there is one neuron for one stimulus. There is a whole family of stimuli that have to map onto a neuron. And that's exactly what the field does for us. So conceptually, it's much better. It requires us to deal with slightly different mathematics, but not really very dramatically. But that is actually the thing that will enable us to go to the robots. These discrete neurons, putting them on the robots, you're confronting essentially that problem. How can you design a perceptual system that makes sure that one neuron stands for something? That's actually hard. You sometimes see neural networks where there's one neuron that stands for a cup and one neuron that stands for or a ladder or something else. And hidden in that model is then the whole problem of pattern recognition or object recognition or segmentation. And of course, that's a bad thing. That's what you want to study. And with the fields, we will be able to link up our neurodynamics to a camera or to low-level sensory input. Same on the motor side. Okay, so let's maybe close here.